Okay, so we're going to start with Lewis dot structures for ions. Okay. So the first one we'll start with is sulfite. What resource can you use to find the formula for sulfite? Okay, so find sulfites on your naming chart. Okay, find the formula. What is the formula for sulfite? Okay, so you should be able to use your naming chart, and you're finding sulfite's formula, SO3 with the -2 charge. Okay, then pretty much the same process until we get to the very end. Okay, so what's the first thing you have to add up? Okay, valence electrons. How many valence electrons does sulfur have?
6.
Okay, 6. What about oxygen?
6.
Okay, 6. And how many oxygens are there?
3.
Okay, 3. And then this part is new. Take a look at the charge. What does that -2 charge mean in terms of electrons? Okay, it gained 2 electrons. So while we're counting electrons, you have to add 2 more. Okay. And again, this 2 is coming from that -2. Okay, so -2 charge means it gained 2 extra electrons. You with me there? Okay, so what's our total number of electrons? Okay, 26 total. Okay, so now we're going to draw the atoms. SO3, which element is going to go in the middle? S, and then we'll place the oxygens around it. And then off to the side, we'll keep a tally. So we started with 26. How many have we used in those single bonds?
6.
Okay, 6, 2, 4, 6. So how many are left?
20.
Okay, 20. Remember when we fulfill octets, always start on the outside and leave your central atom for last. Okay, so oxygen has how many here? 2. How many total does it want? 8. So how many dots do you have to add?
6.
Okay, are all 3 oxygens identical?
Yes.
Okay, so how many dots are all 3 going to get?
6.
Okay, so I'm going to go through and give all 3 6. So we used 18. How many are left? 2. So now I'm going to check sulfur. Sulfur has 2, 4, 6. And how many does it want?
8.
8. So how many do you have to add?
2.
Okay, 2. And we add that in that lone pair. Okay, so again, we know we're finished when our electron tally is down to 0. And does each atom have a filled octet? Okay, last step. Since this one is an ion, you're going to put your entire structure in brackets. And then your charge goes on the outside of the brackets. Okay, so that's your way of communicating this one is an ion. Okay, so now let's take a look at nitrate. Where can you find nitrate's formula? Okay, find it on your naming chart. Okay. Nitrate is NO3 with that -1 charge. Okay, so what's the first step?
How many valence?
Okay, how many valence electrons are in nitrogen?
5.
And how about oxygen?
6.
And how many oxygens are there? 3. Okay, and then the new part is the charge. What does this -1 mean?
Add 1 more.
Okay, it gained an extra electron, so you're going to add 1 to your count. So how many total for nitrate? 24? Okay, now we're going to draw the atoms. Which atom goes in the middle? Okay. N. We'll place the O's on the outside. And then we'll tally off to the side. So we started with 24. How many have we used in the single bonds?
6.
Okay, 6. 2, 4, 6. All right, so how many left?
18.
Okay, 18. I'm going to start on the outside oxygen. It has 2, so how many dots do you need to draw to get it to 8? Okay, are all of the oxygens going to be the same? Okay, so I'm just going to add 6 to all of them. All right, we've used all 18 electrons, except nitrogen has how many electrons around it? 2, 4, 6, and how many does it want? 8. So we're short. So what do we think when we're short? Okay, double bond. It doesn't matter where you put it. Erase a lone pair and draw your double bond. Bless you. All right, so now,
More like a heavy cough.
okay, have we used all 24 electrons? Okay, does each atom have a filled octet? Okay, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Okay, what's the last step for an ion? Okay, brackets, and then put your charge on the outside of the bracket. Okay, so to help me make my next point, how many of you put your double bond between this oxygen and nitrogen? Just like show a hand. Okay. How many of you put your double bond between these two atoms? Good. How many of you put your double bond over here? Okay, notice how in this room, if someone put their double bond in each location, does it matter? Okay. In real life, how do we know where the double bond goes? Do we know? Okay. So this brings me to our next point. So it turns out in real life, the double bond constantly moves. Okay. And when we picture electrons, do you picture them sitting still in your head or do you picture them moving? Moving. Okay. So in real life, the double bond for a moment is between these atoms. And then in another moment it's in between these atoms and another moment between those. Okay. So when we draw these on paper, we call these resonance structures. And we just draw like all valid Lewis structures, okay? And does that make sense? Like the double bond could be between either of those atoms, okay? So you would just have to draw all 3 options. And then in between your options, what is this? What is this right here?
It goes back and forth.
Good. It's like a double-sided arrow, yes? Okay. That double-sided arrow is just showing that this double bond is constantly moving. Okay, so we're going to practice drawing a resonance structure. We're going to draw ozone together. Okay. So again, what's your first step? Okay, valence electrons. How many valence electrons does ozone have? Or oxygen? Okay, and how many are there? Okay, so how many total?
18.
Okay, 18. All right, then this time we can just draw 3 O's in a row. All right, we started with 18. How many have we used?
4.
Okay, 4. So how many are left? Okay, 14. So start over here. How many does this outer oxygen have? 2. So how many dots do you have to draw? Okay. So 6. It has to total 8. Okay. Then let's jump to the outside. This one has how many here? 2. How many total does it want? 8. So how many dots do you have to give it? Okay, 6. Okay, there's 2 left. So let's add those 2 to our central oxygen. But now let's count the electrons on the central oxygen. It has 2, 4, 6. Is that a filled octet?
No.
Okay, we're short, so what should you be thinking? Okay, double bond. So you can just erase a pair and then double bond. So now if we check 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, do all 8, or do all 3 oxygens have 8? Yes. Okay. Now, could the double bond just as easily be on this side? Okay. So now we're going to draw the resonance structure and time me. Time how many seconds it takes for me to draw the mirror image. Okay, how many seconds did that take? Like 5. Okay, so in your head, does it feel like it's all this work that you have to draw another structure? Does it feel like this big task? Okay, but in reality, it probably takes you less than 10 seconds to draw the mirror image. Okay, so even though it feels like, oh my gosh, I have to draw it again, in reality, does it really take that much more time or effort? No. Okay. Let's move forward with some exceptions to the octet rule. Okay. So again, what is the octet rule? Okay. They all want 8. Okay. Some atoms break the octet rule. Okay. So for the rest of the slides, we're just going to go over what are those exceptions. So the first one is, if you have an odd number of valence electrons, are you ever going to be able to fill the octet rule if 8 is an even number? No. Okay. So if you have an odd number, it means you're going to break it. Okay. So my example is NO2. And again, what's the first step? Okay. Always count those valence electrons. How many does nitrogen have?
5.
Okay. 5. How many does oxygen have?
6.
And how many oxygens are there? Okay. So how many total? Okay. First, if you end up with an odd number, double check, triple check your work. It is really rare to get an odd number. So most of the time, if you're on an odd number, it means you made a mistake. Okay, so go back, double check, triple check. Okay. If you've triple checked your work and you're confident you're correct and it's an odd number, then it just means you're going to break the octet rule. Okay. Okay, between NO2, which one's going to go in the middle? Okay, N. I'm going to put my O's on the outside. All right, we started with 17. How many electrons have we used in the single bonds?
4.
Okay, 4. So how many are left?
13.
Okay, 13. I'm going to start on the outer oxygen. How many are here?
2.
2. How many total does it want?
8.
8. So how many dots do you have to add?
6.
Okay. All right, I'm going to jump to this oxygen. How many dots does this one need?
6.
Okay, I'm going to give it 6. So we're down to 1 left. Where does that 1 go? Okay, on nitrogen. So this is the only time it's okay to have an odd number. Okay. So let's count our octets. So oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. And nitrogen has how many? 2, 4, 5. And how many does it want to have?
8.
8. So it's okay that it's going to break the octet rule, but it has to be as close to 8 as possible. Can we get 5 closer to 8?
Yes.
Okay. What number do you think we can get it to?
7.
Okay, so we're short. So what should we be thinking?
Double bond.
Okay, double bond. So I'm just going to erase a lone pair, and I'm going to add that double bond. Okay, bless you. Okay, so now nitrogen has 2, 4, 6, 7. Is 7 closer to 8?
Yes.
Yes, good. Okay, next, let's just look at some other elements that are electron deficient. So boron and beryllium, they can be stable with 6. Okay, so write yourself a little note. Boron, beryllium, if you find them, it's number 4 and 5 up here. These ones are very small atoms, so they can be stable with just 6 valence electrons. And then change my example. We're going to do BH3. All right, so how many valence electrons does B have? 3. What about hydrogen? 1. And how many are there? So how many total? Okay, 6 total. Which atom will go in the center? Okay. B. Then we'll draw our H's. So we started with 6, and how many did we use?
6.
Okay, we used 6. Okay, so do you notice how we're out of electrons? We're out of electrons. Okay. Notice we've only used 2, 4, 6. Do we have any more that we can possibly do anything else with?
No.
Okay, so in this case, because it's boron or beryllium, it is okay. Okay, boron is a small atom. It can be stable. Okay. Now, if you had enough electrons to have boron have a filled octet, would it prefer 8? Yes. Okay, but if you have a scenario like this where you just don't have any more electrons, it can exist with 6. And then finally, if some atoms can survive with fewer than 8, can some survive with more than 8? Okay, so some atoms, in fact, a lot of atoms can survive with 10 or 12 electrons. Okay. So some examples are phosphorus, sulfur, silicon, chlorine. Really, it's a lot of atoms, okay? It is more than this list. And I'll show you, like, how do you know if it's going to break it? We'll do 2 examples, and I'll show you. Okay, so we'll do 2 practice problems. Each of these are different, and these will show you both patterns of how do we know. Okay. So our first one is PCl5. What's your first step? Okay, count those valence electrons. How many does phosphorus have?
5.
Okay, and how about chlorine? And how many chlorines are there?
5.
Okay, so how many total for this one?
40.
Okay, 40. And then if you're looking at PCl5, which one's going to go in the middle? P. Okay, so here's our first pattern. Okay, so P goes in the middle, and then how many chlorines are going to attach to it? 5. Okay, so just kind of spread them out. But by drawing 5 chlorines to it, do you know it's automatically going to break the octet rule? Okay, so if you ever see it's like 1 atom attached to 5 or more atoms, are you going to break the octet rule? Yes. Okay, and that'll be okay. All right, so now I'm going to draw my chlorines. And then off to the side, we're still going to tally our electrons. So we started with 40. How many have we used in the single bonds? So we've used 10, so how many are left? 30. And then we'll start with the chloride. It has how many? 2. And how many total does it want? 8. So how many dots do you have to draw?
6.
Okay. And are all of the chlorides going to be identical? Yes. So how many dots are you going to give each chlorine? Okay, 6. So I'm going to go around and I'm going to give 6 to each chlorine. Okay, we used all 30, so we're at 0. Do your outer chlorines have a filled 8? Yeah, okay. So those are filled. And phosphorus, how many does it get? It has 10, right? 2, 4, 6, 8, 10. And is that okay? Yes. Okay. So again, this pattern is, if it's 1 atom attached to 5 or more atoms, do you know you're going to break the octet rule? Yes. Okay, questions on that one? Okay, let's do XeF4. This one's also going to break it, but it's going to look different. Okay. So what's your first step? Okay, count valence electrons. How many does xenon have? Okay, 8. What about fluoride? And how many fluorides are there? Okay, so how many total for this one? Okay, which one do you think is going to go in the middle? Okay, Xe, and then put your F's on the outside. All right, and then we'll tally. We started with 36. How many have we used in the single bonds? 8. Okay, so how many are left? Okay, 28. Okay, start on any outer fluoride. So fluorine has how many here? 2. How many total does it want? 8. So how many dots do you have to give it? Okay. And is that going to be the same for all fluorines? Okay, so give all of your fluorines 6 dots. So what's 6 times 4?
24.
Okay, so how many electrons do you have left? 4. Okay, so here's the second type of pattern. So the second scenario. If we check our atoms, they should all have a filled octet right now. So I'm going to start here, fluorine. So 2, 4, 6, 8. This one is 2, 4, 6, 8. This one is 2, 4, 6, 8. And this one has 2, 4, 6, 8. So do all of the fluorines have a filled octet?
Yes.
Okay, if we count xenon, 2, 4, 6, 8. Is that one also filled?
Yeah.
Okay. However, how many electrons do you have left?
4.
Okay, can you just make those 4 just poof into thin air?
No.
Okay, you have to draw them. If an atom's going to break the octet rule, it will always be your central atom. Okay, and electrons, do they go solo or in pairs? Okay, so I'm going to put a pair on one side and a pair on just another side. If you chose like the opposite diagonal, is that fine?
Yes.
Sure. Okay, so then because you have 4 more, you have to draw them. Okay, so again, you're just going to draw them as lone pairs on that central atom.